Yeah, so what I'm going to be presenting is Engage Against the Machine, Rise of the Notional Machines as an Effective Pedagogical Device. I'll actually even get my camera back on if that'll show up at some point, or if someone else can turn it on, that works. But yeah, so admittedly, this paper title I suddenly realized might work a little bit better in the US, where Rage Against the Machine is more known as a band, and Rise of the Notional Machines was like the fourth Terminator movie that came out. And I swear, actually, we spent at least half as much time on the paper as we spent on, the paper title. So the question is, why did we actually bother to write this paper? And the reason for it is that while notional machines are a concept that's gaining traction within the CS community, and they see huge possibilities for how it can improve education and improve what we're doing in the classroom, the problem with it is that so much of this really great research is being done just at the cutting edge of what's available, and it's not really as accessible for a practitioner. And since I'm more of a practitioner than a researcher, I know that I have found issues just getting my head around what's going on. And so what we try to do with this paper is take this great concept of notional machines that doesn't seem really well defined and make it easier for your general person who's teaching CS to use. So that's really what we were trying with this. And of course, that brings down to, well, what is a notional machine? So you could say a notional machine is the idealized model of the computer implied by the constructs of the programming language, which is how Dublet, O'Shea, and Monk originally defined it back, like, in 1981, as it says there. This is great, but personally, I found this not as clarifying as I would like. Yes, I can digest the statement if I sit there and read it a good, like, 5, 6, 10 times, but it's just not as clear as I'd like. It's not putting it into practical terms that I can understand. So one of the first things that I know I did when trying to get around this was see if I could understand how everything fit together. And so we came up with this phenomenal diagram that is in no way, shape, or form at all clearer than that original definition. So let me explain this diagram. So theoretically, when we're teaching computer science, we are teaching students to program, that dashed line. But that's not what we're doing, right? Because if we were teaching students to program an actual computer, what we would be doing is talking about registers and the commands going to the processor and everything else, say in CS1, which we don't do because it would be an absolute failure. So the idea is instead we teach them an abstraction. If they set this up, they are storing something with a variable, as opposed to going in, well, as opposed to actually saying it's stored in this register. So the concept of a notional machine is we're going to have an abstraction of the computer. And the big thing about this abstraction is that it is going to be correct in terms of, for the inputs, it gives appropriate outputs. The way that it gets there can be a black box, or it can be not exactly 100% correct, as long as the output is correct. Theoretically, you can have a notional machine that has every single thing for a programming language set up. It could handle every single situation and give appropriate outputs without talking about how it works correctly on the hardware. That gives you some idea of the notional machine. And how does that interact? Well, we've still got our student. The student still has their mental model that has, the part that's right, the part that's wrong. And the idea is that a notional machine hopefully can do a large correct area where they understand how things work and can take a piece of code and run their mental model of the notional machine in order to figure out what the outputs would be without throwing it at the compiler. So yeah, we obviously didn't clarify it as much as we'd like. So let's do a different way of thinking about it. So we're not actually going to try and we don't in the paper define what a notional machine is. There was an entire conference at Dogstuhl about notional machines, and they, who are the experts, did not come down with one single concrete definition. So figured it made a lot more sense for us not to try and do it either. But it's generally agreed upon that the notional machine has rules for how things work in the state of the machine. Whether that is tightly coupled to be a notional machine or whether they're separated is the question, but those two parts are present. And part of what we're doing is we advocate explicitly delineating between visualization tools and the notional machines they depict, isolating and clarifying the notional machines so that it's more apparent, conspicuous, and useful. The idea here is that if those two pieces make up a notional machine, if we think about them separately and we focus on them, we're proposing this idea that it helps how you're going to use them and how you're going to teach. So again, the idea here is that we are teaching something that is simpler than a regular machine. It's consistent with a real machine, but, and here's the big thing, it's just at the appropriate level of detail. I can make a joke about it being, learning to program should be easy, and that's why we're doing this, but yeah, let's take an example. So we've got up here this chunk of code, and with that code, I realize it's not as simple as it might seem, because we just had across the SIGC mailing list a massive chunk of talking about what it means to store a variable. I'm going to sidestep all of that, hoping everyone read it on the mailing list. And instead, let's just take a look at that bastardization of code and see what's happening. We have, for those first two lines, a couple of variables that are getting set. And one of the ways you can think of this is you would have a rule something like whatever value is in the left gets set to a variable name on the left. On the left, that is where you have, something where it's stored. Get to that third line, a rule might be, I'm going to take that num1 and num2, I take my variables and I substitute in the values before I do math using math order of operations. These aren't great rules, and they're not how you would necessarily want to define it for your class, but they are the rules that could be part of a notional machine, how it functions. The visualization can be anything from the cups you see right here, where it's just showing the state of what's happening. When this is done, you'll have something that can store a value in the values that are there. So that's one possible visualization. You could have a different visualization you have right here, where you have the name just linked up to the possible values that are there. One of the things about this is that this is more useful if what you're doing is along the lines of, say, an iterator in C or C++. What happens there is that you might want to say, okay, I is going to go 1, 2, 3, 4. Here's an easy way of showing that state while presenting material. You could also go to what you have here, which is the full-blown memory diagram, where you have even including whether something's on the stack versus whether eventually it'll be on the heap. All of those are proper visualizations for this. And if you think about it separately from the rules, you can see how you can use them differently. If we take it a step further to a slightly more complex example, we have an array that gets set and an array that's reset. Now, if we're taking rules versus this visual representation, and we separate them, think of just this memory diagram, the visualization. If I'm using this in a class that has, let's say, something that's Java or something else with garbage collection, this red line will be here, right? Because when we reset the array, that part of memory gets freed. On the other hand, if we're in a C or C++ where you don't free it, that red line won't occur because instead you just have your memory leak. And the idea here is that, hey, finally got the panel back. The idea here is that when we set this up, we can use this visualization going between multiple courses. So what we can do is we can use the same visualization in CS1, CS2, CS3. So even though we're teaching a notional machine, even though we're using it as a better way of seeing what's going on, we have the ability to go through and use certain pieces, lowering student cognitive load, because this visualization keeps happening. Equally, one of the things about a notional machine is it only has to be an appropriate level of detail. And it explicitly makes you think about what the appropriate level of detail is. So if we look at this memory diagram yet again, we include stack and heap that you might think is not really appropriate for a CS1 course. It might not fit in how you teach CS1. Well, the point of the notional machine, or I should say the point of a notional machine, is that there isn't a single correct one. There is a machine that gives correct outputs for an input. And so the idea is you think of what is appropriate for how your institution teaches. By using the stack and the heap in our CS1 course, it helps set up CS2, CS3, all the rest of them. So it's the appropriate level of detail based upon how we teach. I would argue stack is useful to have there because it makes pass by reference versus pass by value useful. But again, how are you going to use it? And that's where you come back to this idea of the notional machine. So it's like, what's it giving you? It allows students to, again, think about how their programs are actually going to run. It does this while at the same time you can provide scaffolding for later. So like I just said, you could use a visualization between multiple classes. You could look at your rules and point out how those rules are the same between multiple courses and multiple programming languages. So you're setting up the scaffolding as well. Unnecessary detail, if you're explicitly thinking about what the notional machine is doing, as opposed to just using something and calling it a notional machine, if you're thinking about it, it helps you focus on what do your students need? What can you not teach them because it's not important for what you're trying to get across in this course, in this module, whatever. And so by keeping it simpler, by reducing that cognitive load, it should help them create better mental models. So I feel like by explicitly and intentionally separating the notional machine from adjacent concepts like mental models and visualizations, we can deliberately design and use appropriate notional machines at each stage in our teaching and achieve clearer understanding among our students. So with that, I'll open it up to questions.